This presentation aims to answer the question, why study probability distributions? A good understanding of probability distributions is crucial in fields that rely on data analysis, statistics, or decision-making under uncertainty. Probability distributions are used to model continuous and discrete random processes. They quantify the uncertainty in the process. They can be used to analyze data and make optimum decisions in uncertain or variable situations. Practically all fields contain random components that can be modeled using probability distributions. The following list includes typical applications of these models in a selection of fields. Finance applications include pricing of financial derivatives, commodity price forecasting, investment return estimation, portfolio optimization, and calculating insurance premiums. Engineering applications include project scheduling, budget forecasting, project economics, reliability analysis, and quality control. Biology applications include epidemiology, genetics, analysis of medical tests, pharmacokinetics, and disease risk assessment. Energy systems applications include energy resource volume estimation, demand modeling, failure analysis, and process control. Social sciences applications include marketing, urban planning, government policy development, population growth modeling, and income distribution analysis. A selection of typical probability distribution applications are described in this section. Probability distributions model a random process by describing the relative likelihood of possible outcomes of the process. Probability mass functions are used to model discrete random processes, such as the roll of a die or the toss of a coin. Probability density functions are used to model continuous random processes, such as adult male heights. In the first example, a probability mass function, or PMF, is used to model the roll of a six-sided die. A PMF specifies the probability of each possible outcome of a discrete process. In the die roll example, each outcome from 1 to 6 has the equal probability of 1/6, or approximately 0.16666. A categorical distribution is used for this model, with the probability specified for each outcome. The PMF chart displayed below shows the possible outcomes along the x-axis and the probability of each outcome along the y-axis. Note that the probability is referred to as probability mass to distinguish it from the probability density used to define continuous probability distributions. In the second example, a probability mass function is used to model 32 coin tosses, where the outcome is the total number of heads. A binomial distribution is used for this model, where the probability of success, a head, is 0.5, and the number of trials, or coin tosses, is 32. The PMF chart corresponding to this binomial distribution is shown below. Because there are so many ways of tossing 16 heads, this is the most likely outcome with a probability of approximately 0.13995, or about 14%. There is only one way of tossing 0 heads, or 32 heads, so these outcomes have a very low probability. In the third example, a probability density function, or PDF, is used to model adult male heights. A PDF specifies the relative likelihood of different outcomes of a continuous process. Adult male heights can be accurately modeled by a normal distribution with a mean value of 178.4 centimeters and a standard deviation of 7.59 centimeters. The PDF chart corresponding to the distribution of heights is shown below. The height is displayed along the x-axis. There are an infinite number of real number values along this axis, with any particular value requiring an infinite number of decimal places to represent exactly. Any one particular height, selected from an infinite number of possible values, has a theoretical probability of 0. Probability densities, however, are non-zero and are used to define continuous probability distributions. The probability density displayed along the y-axis is the probability per unit of measure along the x-axis. Probabilities are only defined over intervals of possible values of a continuous random process. The probability is the area under the PDF between two output values that define the range. The probability of an adult male height lying within one standard deviation of the mean is 0.6827, or 68.27%. This probability corresponds to the area shaded in red in the PDF chart below. The probability of a height sample lying between any two specified heights can be calculated using this method. Probability distributions can be used to simulate the output of a random process. Rolling a die is simulated below using a categorical distribution model. Pressing the Roll Die button simulates rolling the die, and the result is displayed in the die value text box. Hypothesis testing determines if the results of a survey or experiment are meaningful or not. The following steps are used. Step 1. Formulate the hypotheses. These are two alternate statements about the data, only one of which can be true. The null hypothesis, H0, assumes no effect or no difference. The alternative hypothesis, H1 or HA, represents the effect or difference we are looking for. Step 2. Choose the significance level, alpha. This is the threshold required to reject the null hypothesis. The significance level is commonly set at 0.05, 0.01, or 0.1. This is the probability of rejecting a null hypothesis when it is actually true. A false positive error. Reducing alpha reduces the chance of a false positive. Alternatively, accepting a null hypothesis that is actually false results in a false negative error. Step 3. Choose the test statistic. Choose a statistic that measures the evidence against the null hypothesis. Common test statistics are t-test for mean, compares the means of two groups of values. T-test for proportion, compares the proportions of two groups of categories. Chi-square test, ANOVA, or analysis of variance. Step 4. Decide if the null hypothesis is accepted or rejected. Generate a p-value by applying the test statistic to the results of the survey or experiment. The p-value is the probability of obtaining the observed results if the null hypothesis is true. If the p-value is less than or equal to the chosen significance level, reject the null hypothesis and accept the alternative hypothesis. The t-test uses the student's t-distribution to generate a p-value. If the sample size is large, greater than 30, and the standard deviation of the population is known, the z-test can be used instead of the t-test. The z-test uses a normal distribution to generate a p-value. The student's t-distribution is a generalization of the normal distribution. Both have a symmetric bell shape. The t-distribution, however, has heavier tails. In the figure below, the red curve is a normal distribution, and the blue curve is a t-distribution. The student's t-distribution is named after William Seeley Gossett's 1908 paper in Biometrica under the pseudonym Student. It is claimed that Gossett used a pseudonym because his employer, Guinness Brewery, did not want competitors to know that they used the t-test to determine the quality of raw material. Stock option pricing is a very important application of probability distributions in finance and investing. Fisher Black and Myron Scholes published a formula to estimate the price of stock options in 1973. Robert Merton later expanded the mathematical understanding and applications of the pricing model. The option pricing formula had such a large impact on finance that Scholes and Merton were awarded the Nobel Memorial Prize in Economic Sciences in 1997. Fisher Black died in 1995, before the prize was awarded. The Black-Scholes formula uses a log normal probability distribution to model the behavior of stock prices. Edward Thorpe is believed to have developed the formula in 1967 and used it while running the hedge fund Convertible Hedge Associates, founded in 1969. The hedge fund was renamed Princeton Newport Partners in 1974. The fund returned an annualized rate of 20% after fees for over 20 years and never had a quarterly loss. When a number of standard probability distributions are combined, the result is, in general, an unclassified distribution. Monte Carlo simulations provide a practical way to generate and analyze such a distribution. Oil and gas companies use Monte Carlo simulations to estimate the range of possible oil and gas volumes in discovered fields before making a development decision. An oil or gas field development is a major investment, and the company requires an adequate return with an acceptably low risk of financial loss before making the decision. The following formula is used to calculate the volume of gas that can be recovered from a gas field. Gas volume equals gross rock volume times net to gross times porosity times gas saturation times formation volume factor times recovery factor times 35.3147 divided by 1 billion. The times 35.3147 divided by 1 billion factor in the formula simply converts the calculated gas volume from cubic meters to the standard units of billion cubic feet, or BCF. Oil and gas fields are typically located from 2 to 4 kilometers underground, with their size and shape detected acoustically using seismic surveys. A number of wells provide reservoir depth calibration points and imperfect measurements of the reservoir and gas properties. A digital model of a gas field is constructed using the acoustic imaging data and the relatively sparse well data. Because of the uncertainties in the model, none of the parameters used to calculate the recoverable gas volume have precisely known values. Instead, each parameter is defined by a probability distribution based on the uncertainty of each measurement. It is possible to estimate the gas resource volume using only the most likely values of each parameter. The following formula uses the most likely reservoir and gas parameters to calculate a single recoverable gas volume. Gas volume equals 1 billion times 0.6 times 0.15 times 0.77 times 240 times 0.7 times 35.3147 divided by 1 billion. This calculation results in a resource volume of 411.15 BCF. We will soon see why this single deterministic volume calculation should not be used for an investment decision. The figure below shows the gas resource volume distribution generated by a Monte Carlo simulation. The distribution was generated by repeating the volume calculation 10,000 times, each time selecting at random the value of each parameter from its probability distribution. The 10,000 calculated volumes were used to generate the empirical cumulative distribution function, the red line, and the histogram, the blue bars, which are scaled to indicate the probability density. Reverse cumulative distribution functions are used by oil and gas companies to display the possible resource volumes. In this example, the P90 volume of 249 BCF means that the gas resource volume has a 90% probability of being larger than 249 BCF. Major resource companies require the P90 volume to be profitable before they commit to an investment. If volumes below 300 BCF are not economic, a major company will reject the project because the P90 volume of 249 BCF will make a loss. The deterministic value of 411.15 BCF suggests that the project is profitable but provides no information about the chance of failure. The probability distribution shows that, at the economic cutoff of 300 BCF, the probability of a larger profitable volume is about 77%. Alternatively, the probability of the project making a loss is about 23%. A small development company borrowing money to finance such a project could easily be ruined by an uneconomic gas volume outcome. In conclusion, an understanding of probability distributions is a valuable skill to have in any field. Computer models are used for key activities such as forecasting, scheduling, valuation, optimization, sample analysis, etc. In general, these models should incorporate some degree of uncertainty due to measurement or sampling errors, or forecast inaccuracies. Probability distributions are used to quantify the uncertainties within a model. By building accurate models that incorporate uncertainty, optimum decisions can be made and possible adverse outcomes mitigated.